this f dx is what we started. That was what we kind of based everything off of. So we're just saying we're going to take these integers and look at it in a particular combination. And that combination turned out to be pretty powerful. And it turned out to allow us to kind of do a lot of stuff. So we kind of gave names to a lot of these things. When we put a negative sign here over a certain force, we gave a name to that and we called it the potential energy, et cetera, et cetera. So we did a lot of stuff with that. So what we'd like to do now is we'd like to do some similar kind of rearrangement. We're gonna do something else besides energy, and we're gonna rearrange some things again, and we're gonna see that we come up with some other interesting quantity. So let's take a look at this. I'm going to start this by saying, let's just look at Newton's law. This is kind of the basis of so much of what we do. So this is Newton's law, right? This is basically saying m dv dt. So F is m times the change in velocity over change in time. This is the same thing we've talked about so many times. So what we say is that the force is telling us about the change in velocity. But of course there's also an m here, which is important to note. So we can't say that the force is exactly equal to the change in velocity, right? There's also the m. It's kind of like saying that the sum of the forces tells us about a combination of different factors. The m is one factor and the change in velocity is the other. So why don't we just, the idea is why don't we just combine them together? So why don't we take this m and we put it inside the derivative. So m is a constant. M is not changing as time goes on. So we're perfectly free to move it on the inside of this. And if we do that, then we have the derivative of mv. So it kind of seems like I haven't done anything here, but actually I have. This actually is more interesting. So the reason this is powerful is because I can say that the sum of the forces is directly equal to the change in some quantity. There's no extra pieces that are floating around. It's directly equal to it now. And that quantity that it is a change of is mv. Okay, so we're going to give this a name. We're going to call this momentum. Call momentum. We're going to give it the letter p. And p is just going to be equal to mv. So p has a direction, of course, because v has a direction. The direction is the same. And the value is just going to be p times v. So it's probably hard to believe at this point that this is actually going to be an interesting quantity. I mean, I just took two of the most common variables we had and multiplied them together, right? It doesn't seem like there's a lot going on, but it actually is quite nice. The fact that we've kind of combined these two factors into one really turns out to be a powerful thing. So we can kind of re-express all of Newton's laws in terms of this new quantity, momentum. So momentum is just m times v. So if we were going to re-express Newton's laws, Newton's first law would basically be saying, instead of that velocity should stay the same as time goes on in the absence of external forces, we're now going to say that the momentum should stay the same in the absence of any external forces. And then just like we said before, that when you add in the forces, it's the forces that cause the velocity to change. Now we're just going to say that adding in the forces is going to cause momentum to change. And what Newton's second law looks like is that the sum of the forces in this new terminology would equal dp dt. So all we do is just move the m inside, right? So the sum of the forces tells us directly about the change in momentum. So this is what Newton's second law looks like. And the language of this thing that we're calling momentum. So this would be important for Newton's law. So what about Newton's third law? What does Newton's third law essentially tell us? So Newton's third law is that for every force, there's always an equal and opposite force, right? So this becomes pretty interesting. Let's draw like a simple example here. Let's imagine that I just have like two masses that are connected by a spring. It doesn't have to be a spring, and there's just for some reason, there's a force that's acting on A here. Acting on A, we're going to have some force F. That's the force acting, so maybe it's because of the spring, maybe it's because of something else. But there's an interaction between A and B, and the net result is F. So that means that if I were to add up the forces that are acting on B, then what would it equal? The same thing, right? But not exactly
Negative.
the same. Yeah, it's just a negative of it. So this is just Newton's third law. It says that the forces should be, the forces of B acting on A should be exactly the same as the forces of A acting on B, but I just add a negative sign. It's the opposite direction. So these are going to be, there's always a pair. That's what Newton's third law says. Okay, so Newton's, if I look at this, Newton's second law is telling me that the forces are telling me about the change in momentum, right? So this force right here should be telling me about how A's momentum is changing in time, right? Likewise, this guy right here should tell me about how B's momentum is changing in time, right? And I can say that the relationship between these must be what, then? They're going to be equal and opposite to each other. If the forces are equal and opposite, and the forces tell me about the change in momentum, then these momentum, the change in momentum of A has to equal the negative change in momentum of B, right? If we just rewrite this a different way, just move it to the same side of the equation, then this is like saying that this is true. Just moving it to the other side of the equation, right? And then in fact I could take this a step farther and I could factor out the derivative. And the derivative is a linear operator, so I can, of course I can write this like this. So that the derivatives acting on the sum together, right? So this is really significant because this is saying that the total momentum, and on my system here, this is A and B together, total momentum. This is not changing because if I take the derivative of the total, then it has to be 0. Basically saying the total momentum P is not going to change. So this is really important. So this is basically saying Newton's third law essentially is saying that momentum is conserved. It's saying that for every decrease in momentum somewhere due to the force, there's going to be a corresponding increase in momentum somewhere else. So there may be exchanges of momentum among different objects, but it has to be conserved. So this is, as I said before, this is one of the most important laws in physics because it's essentially saying momentum is conserved. Because the total not changing. So just like with energy, when we did energy, we kind of rearranged things according to a certain particularly interesting quantity, and we came up with a conserved quantity. It was really useful. Conserved quantities are really easy to work with. They're very conceptually easy to understand because you can imagine. Like with the cups, you can imagine there being a certain amount of energy in different piles, and those like cups kind of exchanging energy with each other. And it's also easy to calculate with because we can kind of fixate on two specific points, an initial and a final point, and just write out the energy for each side. Now we can do the exact same thing with momentum because we see there's another conserved quantity. Again, we were clever. We're kind of rearranging it. It seems kind of minor, but we are doing a rearrangement here. We're going to focus not on the velocity anymore, but combination with the velocity. N times v is going to be the thing that's really interesting. But by doing this simple rearrangement, we're able to see that we have another conserved quantity. The momentum is going to be conserved now. So it's really, really powerful. Okay, so we have a law. This is basically the law of conservation of momentum. It always stays the same as time goes on. I thought now it might be a nice opportunity for us to just kind of do a couple simple questions. So let's take a look at a couple of questions here that come up. Those. Okay, so the first question is, imagine that you're stranded in the middle of a lake of ice. In other words, it's imagine that the friction is completely 0 on the lake. Can you think of a way, like, how would you get to shore if you were stranded there?
Throw your shoes. Yeah. Throw whatever you got.
What?
Take.
Yeah. So
Throw.
how do you propel yourself forward?
Throw
We're
whatever.
going to slide across the lake, right? How do you propel yourself forward?
Throw whatever you have backwards.
You're trying to push with your foot, and your foot's just going to slip on the ice. You don't have any traction. So yeah, you could use something sharp if you have something sharp. That'd be kind of like increasing the friction in the ice. You can kind of make it rough.
Use your nail. Swing your legs.
So you can swing around, it's not going to do anything, right?
Throw your shoes.
So what does momentum tell us why this doesn't work? Momentum tells us that I can't walk to the edge, even if I'm really careful. And my momentum can't change. What do I need to change my momentum? I need an external force, right? So this should be helpful to say. So any internal force is not going to do anything because it's only basically exchanging. If I have a system and there's an internal force between two objects in that system, the total momentum between them will not change because it's just an exchange. They might be exchanging momentum between each other. The total will not change. So I need some kind of a force that's coming external to my system. If there was an external force to A and B, then A and B would be changing. Of course, then we could say that the bigger system is still not changing, right? But more localized, it can. So we need an external force. And usually when we walk around, then what force is propelling us?
Friction.
Essentially what kind of friction?
Static.
Static, right? So my foot doesn't actually slide against the ground. It's sliding when I do this, but when I walk it doesn't slide. So it's static friction which propels the force. That's how I move and how I stop. So if I'm on ice, I can't do that. So is there any way that I can create like an external force if it's just me sitting there?
Do you have anything? Throw whatever you have.
Carlos, you were kind of saying this, right?
Yeah.
Can you say it louder?
If you have shoes on or whatever, you could take them off, throw them backwards, and then they'll propel you forward.
Okay, so what's going on there? So I'm going to take my shoe,
Yeah.
and I'm just going to throw it.
Yeah.
And that's going to get me to shore?
That's gonna propel you with the opposite way that you threw it. I don't know if it'll get you to the shore, but.
So how do I think about that in terms of momentum? What's going on there?
You have your shoe, mass, and velocity.
You gave it momentum.
You get yourself velocity.
Right. That's right.
Yeah.
So the idea is we would say we have the same momentum, right? So the momentum of me and the shoe is going to be the same, right? As before, it'll still be zero combined. But I'm going to throw it. The shoe's going one direction, and I'm going the other direction. So eventually I would get to shore. And I have to walk around the other side of the lake to get my shoe. Right. So here you can see that the direction of momentum is really important. We can have momentum going in opposite directions that add to zero. So the initial and the final is still going to be zero. There's no external forces, so momentum is telling us they should be the same as before, which is zero, right? And it will be zero in this case, it's just that we'll be going opposite. What will be my velocity relative to my shoe's velocity? How do they compare? Slower because why?
The mass is greater.
Yeah, the shoe is much less massive.
Yeah.
So its momentum which should be equal, right? So if my mass is a lot bigger, my velocity will be a lot lower. So you can kind of see momentum is kind of giving us some, if we kind of think about it from a momentum perspective, it kind of gives us some insight on this. So that's right. That's the idea. No external forces, but I can kind of throw something, propel myself. That is true. Okay, so that's one. Another one is, say you're in an automobile accident. People oftentimes say that you'd be safer if you're in like the heavier vehicle. So do you think that that is true, or do you think it's not true based on the physics we've learned in the course? Maybe think about this one for a moment to yourselves before you answer. Kind of think about